Who has a glass of Guinness, porter, stout in your hand? This place that we're in has been serving beer, stout, for 182 years in various forms. Apparently, stout keeps you fit. And you might wonder why you need to be fit. But this is the place to be, because the stout here has been famous. It was known to be highly viscous, thick, bitter, cold, and fortifying. Here we are. We're right here. This is 1949. Things have changed a little bit, but the idea was the following. You would fuel up at the service station next door, and then call in here to fuel up with a very strong stout to fortify yourself for the road ahead to Parramatta or beyond. 1949. Here we still are, but of course things have changed. It's very interesting to think about the device in your pocket and how that looked in 1949, a little closer to something like this.
That's a big pocket.
This is Australia's first computer, 1949, that ran a program. It was the 5th digital electronic computer in the world and the first computer to be used to generate digital electronic music. But it turns out, at this time, it was rather difficult to get your hands on one. There were 5 in the world, so not so easy. A New Zealand farmer, some years before, became pretty interested in computers, what they might be able to do, and also very interested in economics, and thought, I wonder if I could use a computer to help visualize, demonstrate how an economy works. Came to Australia, but couldn't get any time on this thing. Approached the University of Sydney School of Physics, but they didn't have a computer yet. In fact, they were a little bit upset with the ornery kind of characters that were running this machine and decided to build their own some years later. Bill Phillips, the New Zealand farmer, ended up at the London School of Economics, where he built his own computer, but not out of electronics, but out of fluids, tanks, pumps, tubes. This thing was meant to be the pinnacle in science communication. See, it was very difficult to explain how an economy worked, and he thought if you could watch a fluid going around, you might see. You can see here there's disposable income, it comes down, it's consumed, there's domestic spending, and it pumps it back up, there's taxation, and so on. What a fantastic visual aid.
Wow.
But as it got more complicated, it wasn't so easy to really understand how this thing worked. In fact, it was probably the biggest failure of science communication. Where it succeeded, although it was difficult to understand, was that the thing started to actually be able to predict and model and compute how economies worked. They had the idea that they'd take 2 of these machines, join them together with a big pipe, and see how tariffs might affect different countries. That might be relevant today. This is the Federal Reserve in the UK observing for the first time the dynamics of these 2 machines wired together for the first time. It became a tool to understand and predict how an economy evolves. Challenge was, though, if you think of about an economy, a modern economy has a lot more than just the dynamics of the fluids. There's friction. There's personalities, there's governments, there's froth and bubble and viscous behaviors and memories. Why not replace the water in that fluid machine with something a little thicker? You guessed it. They filled the machine with stout and found that within a few percent of accuracy, it could reproduce the historic record of how the economy was working in the UK. How about quantum mechanics? Materials, chemistry, cosmology. We're trying to simulate the behavior of these types of exotic and complex systems. And at the moment, we're trying to do it with digital electronic computers that are inefficient at solving these types of problems. Why not build a computer that's built out of the same physics of the thing you're trying to solve? Instead of a fluid and the Navier-Stokes equation for fluid dynamics that's allowing us to understand an economy, let's build a machine that at its heart is built from the physics of Einstein, not the physics of Newton. A quantum computer, like that fluid machine, is a computer that's trying to now understand the exotic behavior of these quantum systems. But, like our science communicator, this is a pretty complex thing. Where we stand today is this is looking awfully complicated, hard to understand, and we've realized that the future, in order to be able to realize the dream of scaling these systems, is to in fact simplify it dramatically. We've got to get rid of all of these wires and cables and pumps and pipes and turn it into something that's a little closer to the devices in our pocket. This event is sponsored by S3B, the Semiconductor Sector Service Bureau, whose mission is to build an ecosystem of people who know how to design chips, manufacture them, and build out in Australia a capability to see that technology used to build quantum computers and many other areas of technology. At the University of Sydney, we've been very much in this mindset. This is a dilution refrigerator, and I'm sure many of you have seen them before. I showed you one just a few slides back. I frequently get the comment that our fridge looks very boring. Did you just take it out of the box and take a photo? That's the whole point. It's free of those cables to a large extent. Instead, at the bottom there, near absolute zero, you'll see some chips, qubits, controlled not from room temperature, but controlled now via chips, silicon chips that operate close to absolute zero and autonomously manage a lot of the signals and communication that's needed. Famous hands there, Alexis. Happy birthday, Alexis! I've spent the last nearly a decade working for Microsoft as well as the University of Sydney. That has certainly positioned at least me and a large number of people who are here tonight to think about how we might, in Australia, in Sydney, create something that is really oriented to this mission. Building a quantum computer, scaling a machine that emulates and simulates, computes with the same language that nature uses in quantum mechanics. We're interested in computing in general, not just quantum systems, and thinking about what the future looks like for these types of systems. So I think looking back, 1949, things have changed dramatically in terms of computers. It was a different world. But I think the next 75 years, you're going to see even more changes, and it's probably a good idea to fortify yourself for the journey. Thanks very much.
Thank you.